All right. How you doing, Professor? Coming through?
Yeah, we're coming through. All right. And I'm coming through.
Yeah, a little bit low. Hold on. See if I can get you. All right. One more time.
Testing. Check 1, 2. How's that sound? Am I
I
coming
was going to
through
jack
okay?
you up a little bit. Come on.
Let's see if I can.
Yeah, it should be. Should be good.
Okay.
You're on the first quiz.
Yeah, I've got my microphone volume pretty far up. So, but it's good. All right. So now we're recording. So, and hopefully you're seeing my screen now. I'm going to go into present mode. Come on. And hopefully you're still seeing it, right? So lecture 5, receiver design. So we'll talk a little bit about the kind of conceptual function of a receiver. We touched on this in our first lecture. We'll go a little bit deeper, talk about RF receiver block diagrams. It's more of a circuit approach, but will help you understand where some of the impairments come from that we'll deal with. We actually kind of assume some other engineer has handled all that part of the process, and we'll focus on things after that first level of processing. But I think it's important to be able to put everything into context. And we'll look at some of the impacts of these impairments on the constellations that we've been looking at the last few classes. And then we'll talk about some optimal receiver designs from a mathematical random process perspective. So, okay. So the function of the receiver, we've already seen this diagram here. Now we're going to focus on the receiver, and of course its job is to estimate the information sent. That information can be described as entropy and that type of thing, but if the receiver already knows the information, there's no need to send it, right? So we talked a little bit about that at the beginning. So there's obviously some uncertainty. That's why we need to communicate it. So the receiver is trying to do its best to estimate what was actually sent. The challenges are that there's a lot of impairments, a lot of things that can go wrong through this whole process. We've talked a little bit about noise. Noise originates from the random motion due to thermal effects, anything above 0 degrees Kelvin. And so you ultimately have charges that are moving infinitesimally small, but they're still moving. And that movement of a charge is current. It's the definition of current. And if you have a non-zero voltage at the input of your receiver, that current will generate noise as a voltage, and then that'll get amplified and processed along with the rest of your throughout the rest of your receiver, just like your signal is. So the signal is attenuated as it propagates from the antenna or the source transmitter to the receiver antenna. You studied that a little bit in EM fields, perhaps, and you know that whatever field was generated at the transmitter antenna, as it propagates away from that antenna, it's going to spread out in space, right? It's not like a laser. By the way, a lot of this that we talk about can be applied to optical or laser communications, but if we just look at radio type communications right now, then as that wave travels away from the receiver, it's spreading out in all transverse directions, right? As it propagates longitudinally out from the antenna, out away from it, it's spreading out more and more. So there's an R squared at least dependency on the wave magnitude. So it attenuates, even if it's not going through any lossy type of media, right? So we also have distortion. I've mentioned a few times that there's distortion in particular in the power amplifier of the transmitter. There can be distortion in the receiver also. And there can be fading, multipath interference when, in a simple case, if you assume that from the antenna, between the antennas, there's a direct path, and then there's also a reflected path. Let's say it's reflecting off some big building or a mountain or something like that, some walls inside. Then that reflected path is going to take longer to get to the destination, means it's going through more phase shifts. And so when they combine at the receiver antenna via superposition, they're going to combine, the phase may or may not cause some cancellation. There's going to be some vectorial addition. And if the phase is opposite, it's going to create more of a null. If the phases are in phase, then it's going to be additive. But of course, there's every combination possible of those phases from 0 to 2 pi, right? So, and in a mobile communications situation, that is constantly changing. So you will have what we call fading or dropouts due to this multi-path interference, multiple paths in that transmission link. And of course, we also have interference from other users of the spectrum. And so in an unlicensed band, they may be in our same band, and we all have to kind of get along somehow. In an unlicensed band, generally you have, as a licensee, you have full rights to a certain chunk of spectrum. But when we transmit, our energy doesn't always stay where we want it to. And so we have some leakage. The regulatory agency in the US, that's the FCC, the Federal Communications Commission, they will typically prescribe a spectral mass that says outside of the spectrum window, all the energy has to be down below a certain field strength. Okay, but it's still there, right? So we still have to deal with it. So the receiver might have a good knowledge of the transmitter, but a poor knowledge of the channel and these impairments associated with the channel. And as we noted before, it has a poor knowledge of the information that's sent. Otherwise, there wouldn't be a need to send it, right? So it doesn't know the information being sent. It might know the set of symbols that are possible to send, but it doesn't know which particular one was sent at a particular time. So the receiver attempts to learn something about the channel so it can compensate for its effects. That typically knows something about the signal from the knowledge of the transmitter design. We often put structure into the waveform design to help the receiver learn about these channel effects. So in, let's say, a 5G cellular 3GPP type of waveform that is, we commonly know as LTE, 5G version of that, then there's, for every frame of transmission that's transmitted, there's some well-known synchronization sequences at the beginning of that. I'm not going to test you on this, but I think it's useful to have a good context of this, right? So there's some well-known sequences at the beginning of that frame, and then the receiver can look for those and synchronize its timing associated with that, right? So it knows when a frame is beginning. And then there's also some what we call pilot tones or reference signals. I think they're called reference signals in the LTE standard, that are distributed throughout the waveform that don't carry any user information. They carry signal strength and position within the frame so that the receiver can look for those well-known signals and calibrate itself to that, right? So ultimately, we're limited by the amount of noise relative to the signal power. So we're going to try to compensate for a lot of these effects. And we'll talk about a few of these techniques in the course. But there's a lifetime of study available to you if you go into this as a career or go into grad school. There's a lot of very interesting techniques to do all these compensations. So now to go back and review this expanded model of communication system, again, we have this transmitter. It goes through the channel. The digital demodulator estimates which set of bits correspond to the received symbol. And then we try to do some error checking with some basically like parity check bits and that type of thing, and then process it for output, right? This is more of a circuit or a block diagram approach at a very simplistic receiver. And we would start with the antenna. Of course, the electromagnetic waves induce current into this antenna. Then we will typically have some sort of filtering function up front between the antenna and the first amplifier. This is intended to attenuate or reduce the strength of interfering signals so that it's only passing the desired signals into the system. And that's to prevent some nonlinearities that might occur in the low noise amplifier. That's this next block here. This is designed to be a very linear amplifier, but we can only ever be so good at that, right? There's a lot of trade-offs involved. And so if you put multiple strong signals into that amplifier, then you will drive that amplifier into closer to saturation into its nonlinear zone. So it will begin to compress, and instead of having a gain of G, it'll have something less than that. And because it can't keep producing infinitely greater output power. So it enters a nonlinear region. And now in this case, superposition no longer applies, right? So your signals don't just add, they actually multiply. And so when you do that, you've got two signals at different frequencies, then they will mix and cause some additional interference terms. So that's that purpose of that initial low noise, low loss filter up front. So we try to make this as low noise, low loss as possible, because any loss up front affects the noise performance of our overall system. This first amplifier is critical to the overall performance of the system, and we need this amplifier to be very low noise, or to add a minimum amount of noise to the signal as it amplifies it. So once it gets through that first stage, then your noise, it dominates the noise performance of the system. So if you do a good job up front, you don't have to worry so much at the back end. We might have a chance later in the course to put some math to this and describe that. But just conceptually understand that the earlier part of our system, the part of our system that's closer to the antenna, that is going to set the overall noise performance of our system. So we want to be particularly good in that region. So the signal comes in at a RF frequency that's, you know, a function of the spectrum that you're allocated. That might be around the Wi-Fi frequencies at 2.45 gigahertz or 5 gigahertz, or it might be in a millimeter wave area that's being allocated to some of the newer 5G type things, and that would be in the tens of gigahertz range, or it might be a more designed for long range communication that's more effective at lower frequencies, even as low as let's say 10 megahertz or so. All right, so that signal is coming in at RF frequency. We want to move that down to more of an intermediate frequency where it's easier to implement our digital signal processing. And so we create a signal that we call that the local oscillator signal. And we then create the signal close to this frequency of the RF signal. And then we run both of those signals into a mixer. A mixer is purposely designed to be nonlinear. And in this case, the signals will multiply together. And if you work through your trig identities, you figure out that the output of this nonlinear device will be the original signals, but also the if you look in the frequency domain, you will see signals at the difference frequencies between these two and the sum frequencies of these two, right? So if this is at FRF and the local oscillators at FLO, then the outputs here will be FRF minus FLO. There will be a signal here at that frequency. And we design the separation of these so that this is down at a more convenient frequency, let's say in the megahertz range or tens of megahertz range, and all is a convenient part of it. Now we will do some more precise filtering. This filter at the beginning of the receiver is just trying to do kind of a quick and dirty job of getting rid of the interferers. This one here now is going to be designed to pass your signal and only your signal, and reject all the other signals. Can you still hear me?
Yep.
Okay, good. I just got to notice that my microphone changed for.
Oh, we lost you.
Oh, there we go.
In and out a little bit.
All right. Okay. All right. This is not good. Let me. Testing one. Right.
Not really, no. Can't hear you.
How's this? Can you hear me now?
Oh, yeah, that's perfect. Yep.
You can hear me now. Okay. All right. So the this filter, we call it the IF filter. IF is short for intermediate frequency, and it's going to select only your signal, and any noise and interference outside of the spectrum that your signal occupies will be rejected, ideally. Okay. And so then now we're kind of ready for the rest of the story, right? So at this point, we'll possibly earlier, but in this area, we'll do a conversion from the analog domain into the digital domain. We'll do that with a sampler and EDC, and sample the signal and quantize the signal. And now we're working with words of data formed from a set number of bits and stuff. So all right, so let's look at what really happens in real life. I just found some of these plots off the internet. This one is actually looking at a laser communication system, but the same principles apply here, in that we end up with this looks a little bit more like the constellations we saw earlier. These on the right hand side, this is going to be 64 QAM, QAM. So because there's 8 here times 8 here, so there's 64 different constellation points. What we're seeing here in this lower right hand chart is kind of similar to what we saw before. The colors, of course, are just for visualization aspects, but these are no longer these kind of ideal little points that we would see. By the time they get to the receiver, they're starting to smudge or smear a little bit, right? And this is primarily due to noise. Noise of some origin, typically this additive white Gaussian noise, thermal noise, but also some other effects that we'll look at. The this one on the bottom right has a optical signal noise ratio, but the same concept applies in the RF domain, of 28 decibels. Okay, so the signal is 28 dB stronger than the noise. That's a lot. This one is only 22 dB stronger than the noise. So here you see that while that smearing or smudging, the spreading is right at the edges of these other constellation points. And you can imagine if the signal noise ratio gets any worse or less, let's say down to 20 or 18 dB or something, then you're going to have a lot of these points being confused. The receiver is going to confuse them with the wrong constellation point when it tries to make a decision. Was that that original point transmitted here or there, right? So so this helps you understand the impact of noise. Now, what are these on the left-hand side? Well, when you transmit your signal over a channel and you receive it, you don't know exactly how many wavelengths that channel is in typically, right? And it might be changing, right? If you're in a mobile communications type situation, the path length in measured number of wavelengths or the number of phase rotations, a wavelength of propagation means that your signal is going to cycle through 0 to 360 degrees or 2 pi radians of phase shift throughout a wavelength. And so when that gets to the receiver, there might be some arbitrary phase that has been added to this constellation. It'll cause a rotation, right? Remember, we're looking at this in a complex plane. And if instead of looking at it in a Cartesian coordinate, we look at it in a more of a phasor or a polar coordinate type of situation, then we realize that, yeah, the rotation about the origin is very, very sensitive, directly sensitive to the phase of the signal. And if that phase of the signal changes because we've changed the path length between the transmitter and receiver, then that signal will rotate around the center or the origin of that complex plane there. So that's what we see on the left-hand side, where there's been a variety of different rotations. Okay, so well, now it's saying my meeting's going to end in 10 minutes, so I may have to start this up again. So fun with online learning here. So the phase then is rotated, and the way we get these constellation plots is that we record the reception of many different symbols that are transmitted, right? So these aren't transmitted all at the same time. This is kind of a cumulative record of the symbols that have been transmitted over a period of time. So that means that in these left-hand cases, these have suffered all sorts of different rotations, and therefore we have to lock onto that carrier and try to remove these rotations. So we have circuits or algorithms in a receiver that move us from the left-hand side here to the right-hand side. That local oscillator that we described is not a perfect oscillator. It has some noise in it. Now, an oscillator normally operates in a saturated mode, amplifier mode, and so its output power doesn't change that much with respect to noise, but its phase does. So that's how noise manifests itself in an oscillator, is typically through the phase of the signal coming out, moves or jitters around a central value. And this ends up being imparted on the signal in that mixing process. And so by the time your receiver circuitry is looking at it, it is jittering around here in kind of small random rotations. Okay. So Charles, I'm going to send you another Zoom link in a moment here, and we'll have to jump to this other thing because my Zoom is going to end here in a few minutes.
Okay, sounds good. I'll give the students a 5-minute break. Just to
yeah, that'll work. So we'll just go until it cuts me off. So sorry about that. I'm used to working with a licensed version at work and didn't remember that this is time limited. So all right, so our waveform and channel models, we're going to look at an additive white Gaussian noise channel, which has its sole effect as the addition of white Gaussian noise processed to the signal in an additive or linear way. Basically, we're talking about superposition here. So all those other impairments we talked about, we're going to ignore for now. Okay, and we're going to look. We can look at this in the as a time domain signal, but we also talked about how we can look at this as a vector also. especially in digital communications where we have samples, right? So we organize those as vectors. Sm of t is a transmitted signal drawn from m possible signals, or signals that match the symbols. And nt is a sample waveform of a zero mean white Gaussian noise process. And we talked earlier about how we denote its power spectral density as capital N naught divided by 2. And R of t is the received signal. So N of t is a sample waveform of a this noise process. And if you repeated your experiment, you would get a different sample. So it's a random process. All right, so our receiver observes R of t and makes the optimal decision about which message M within that 1 to capital M set was transmitted. Right, so the optimal decision is a decision rule that results in minimum error probability. Now, some of this is kind of obvious, but it's helpful to really be precise in our definitions. So our probability of error is equal to the probability that our estimated M is not equal to the true M. Okay, so we're going to use this little caret over our letters to designate things that we're estimating at the receiver. So signals are values, and this is used to distinguish them from the true values, right? So M without a caret or a hat on top would be the true message that was actually sent, whereas M hat or M caret is the one that we're estimating at the receiver. Obviously, we'd like those to be identical, but not always going to be the case. So we can talk about a general vector channel. So we can describe our channel and our receiver process in terms of these vectors. And so M is chosen 1, 2 to M based upon the bits that are coming in, but we describe that as a probability of which M will be sent, right? So on a transmitter, it's transmitting some number of bits, mapping those to symbols or messages M. It's picking out a particular M out of the set of capital M different symbols and sending that. Well, we describe that process with a probability P sub M. And our vector N there is composed of Nj, where that goes from 1 to capital N, or IID, commonly annotated, standing for independent, identically distributed noise, zero mean Gaussian random variables. Okay, these are noise samples. So they're all independent of each other, and they are identically distributed, meaning that they have the same variance. And well, they're zero mean, so they're all going to be zero mean, but they do have the same variance here, described as n naught divided by 2. Okay, so we can describe the PDF, or the probability density function, then as of n, of this random variable n. And because there's n of these, capital N of these, they're going to combine, multiplied together. They're independent, so we don't need to worry about any conditional probabilities. We just multiply them together. Up in the exponent, those are just added because they have a common exponent. But for the coefficient up front, that becomes exponentiation. So this is multiplied n times, right? And so this is the Gaussian distribution multiplied on itself n times, or to the nth power, right? So we can notice here that this is basically the norm of these these NJs. So that's just a notation change there, and we've got this 2 sigma squared down there, but we can do some substitutions and replace that with N naught based upon that notation that we keep track of right there. So all right, why don't we stop right there, and we will take a very short break, and we will start back again in a few minutes. Okay.
All right, sounds good. See you soon.